Hey everyone, welcome back to my channel EduVibe. In today's lesson, we are moving to another topic of the atomic physics, which is the isotope stability. In that, we are involving some like graphing thing of the decays, alpha decay, beta decay, and gamma decay. Not the gamma decay, but we do with the alpha and beta. So these are graphs very easy. You have to you want that like direct question to make the graphs. You get like a different questions like something else. I will tell you that. So isotope stability. So what is that thing? So the lighter elements tended to have very stable, and when the neutron and the proton ratio is roughly 1:1, when we get the heavier elements, which is the stable elements, tend to have a neutron to the proton ratio approximately 1.5:1, 3:2, you can say. So what they tell that the lighter elements have this thing, the neutron proton ratio, which is a 1:1. But when they have them, when we have heavier particles, they tend to have a neutron to proton ratio of 1.5:1, which is 3:2. So that because of that the difference of the ratio from neutron to proton, we will discuss the belt of stability. We will use a belt of stability to predict what type of decay a nucleus will undergo. In the heavier or the lighter particles, whatever decay is going on, and we for this analysis we do some the belt of stability. What is the belt of stability? So this graph is for isostability and also called for a belt of stability. So this graph telling about that which decade has which element has the which decade, alpha decade, gamma decade, and everything. So isotope stability, the dots on the graph represent the belt of stability. That dots are representing the belts of stability. And the solid line represents n is equal to z. This solid line represents the n is equal to z. Maybe with another color, this line. And the dash line is barrier. This is the barrier. This line is the barrier of that. Stable isotopes have been absorbed for isotope 83 or the more protons. So the belt of stability must be end here. So you have to find that what is that regions called. So the region a nucleus has too many neutrons. In region A, we have a neutrons. We have only the so many neutrons in region A. To achieve the stability of this, it will likely undergo a beta negative decay. So in this A thing, we have a more neutrons, and to achieve the stability of this, we have a beta negative decay undergoing in region A. In region B, this has too many protons. So region B has too many protons, and also to achieve the stability of this, they will use the beta positive decay. They will likely to undergo beta positive decaying that. And for region C, we have a nucleus has too many nucleons. So in this C, we have this is a nucleus has too many nucleons, and to achieve stability, they will undergo alpha decay. In the C, you have alpha decay going on because it's after the barrier. So there's a nucleus with too many nucleons, and they will achieve by the alpha decaying. So that's the whole thing. You have to know that what region represents what. But you can't write the question like directly from here. You can write the like one question, like simple question you get from MCQs. But you will get a question like this too. Radioactive decay series. This is again related to radioactive decay types. When a radioactive nucleus decays, that is usually not the end of the story. The daughter nucleus itself is often the radioactive, which means it will be decayed. The daughter nucleus is also, when we get the product, the daughter nucleus then also further be radioactive. So it can means it will be decayed after that. If it decays into another unstable nucleus, it can be continual pattern of the decays, and the point of stability is finally reached. So the first decade we have over there, then that daughter nucleus then do another decade. So they do another decade. They do decays and decays, and the continual pattern like this. This is called the radioactive decay series. The entire process is called the radioactive series. The chart on the right shows the radioactive decay series for the uranium 238. This is the uranium 238 chart. It has many different paths that it can take to get to a point where two stable nucleus is reached. So there are many paths. They go over there. The arrows represent that. So they're over there, then go straight over there. And to reach that point, to reach to reach the stable, which is the lead 206. They reach over there. The important point to note is that there is a many paths to get to endostable nucleus. The part taken to one by the laws of probability. These are all by laws of probability. The graph is the thing to like reach to the maximum stable nucleus point. That's the main thing. So we have one example of there to make this actual graph. How can we make that graphs? And we have a graph too to make this. So how can we make this? Let's see and make that. So one decay series for the Neptunium 237 results in a stable bismuth 209 nucleus in 11 steps. So in 11 steps, you get from here to here. These are the steps. They go with alpha, beta negative, alpha, alpha, beta negative, and then it goes on. Show and complete the balanced nuclear equations for all 11 steps and stretch the decay series graph below. So to find the, you have to make the graph also. And firstly, you have to do the equations that reach to that point. For the AU step from MP, which is the Neptunium 237, and you have this 93 atomic number, and you will reach to the alpha 42 plus you will get a PA 233 minus 4 and then minus 2. Then we have a B. We have another thing. So with PA goes on over there. So PA, which is 233, now 91. Now it goes the beta negative. So according to that, we have this. Plus we have a this U. So you can check this from your periodic table. I will just do the equations directly, quickly. You can check that what thing is what. Done. So this is beta negative and you have this line over there. Done. Next, we have a U233 and this is 92. Again alpha, so it's alpha 42 and we have plus, you will get a which is 239 and this is 90. Yeah, this is 229. Then let's do from here. Then here we have TH 229 and 90. This is gain alpha thing. So we have alpha 42 plus RA 22588. Then we have RA which is 22588 and you will get a beta negative now. So that thing, you get something AC 22589 plus this. Then we have AC which is 22589. This is going to alpha decade again plus F or something 221 and we have 87. After FR you have 221 FR 87. This is again alpha decade, so this plus 80 you get 217 and you get 85. Now I'm moving over there. 85 217, this is 85. So this is again alpha decade and plus BI 213 83. You have start doing this and there are 11 steps to reach over this thing. Again we have BI 213 83. This is going to beta negative decade. You get 213 84 plus the neutrino. Then this thing, which is 213 84, going to the alpha decade again, and you will get a PB 209 82. Last also, they go into the alpha decade, beta negative decade, and you will get a BI 209 83 plus neutrino. So that's the 11 steps, and from that 11 steps, now we have to make this graph of this. How can you make this graph? So firstly, so I will tell you the first one. So this is MP, they start from MP. which is that over there, this 93. Now this is alpha decade, and from 237, from like, so you can say the atomic number from 93 it goes to 91 with 237 to 223. So over there you have a 237 over there, your atomic number, and this still goes to the 233, which is over there, which is like this. So you have to put arrow like this, they go down, and we have alpha. So it also goes from 93 to 91, you can say. Next we have a beta negative. So it goes from 233 to 233. So it stays on 233, but they'll go from 91 to 92. So now they go backward. So as this is over there, this over there. So from 91, so 91 they go 92. So this is 91 and this is 92. They go over there, but remains in the same state of this, which is 233. So after that you can do this all the thing up to this. So again you will get this type of arrow, you will get this type of thing. You have made by your own. I will just make the roughly thin that thing, so you can make the more accurate thing of this. You can just make it like this, and at the last this stays like they reach over there, that B3. At last they have a beta negative. So this is a roughly thing, not like follow this thing. You can make by your own, like I will tell you that how can you make first two, and you can start doing with all 11s, and then you reach over there at the end. You will reach that this thing, P33, which is 209. So that's how you can do this graph, and you cannot get that graph question directly. You can just do some theory, you can memorize some theory and that part, isotope stability, and that's all thing. You can't get the to make the graph directly in the written response. So that's all for this lesson. So isotability is not very important topic in that lesson. The next topic we are doing, which is not now from the data decade, from the activity of the half-life. Very easy topic, very small topic, and we discuss the topic in the next lesson. So let me say where to why learn from not harder. Please like, share, and subscribe to my channel. If you have any questions, let me know in the comment section. See you in the next lesson. Take us created with EduVibe.